Okay, for our R of t function, it's very easy to calculate the velocity function. Just take the derivative of the R of t function, you come out with this. The acceleration is just the derivative of the velocity function. The I and j components are constant, they have derivative 0. The k component derivative is going to be 0.04 times k. The unit tangent vector is nothing but the velocity vector divided by its magnitude, and I believe I have the magnitude correct. So there it is. And of course this could be expanded, and if you want to take the derivative of the unit tangent vector, it'd be worthwhile to expand this. Okay, the component of, okay, well, there are the three vectors that we want to work with. And I think we talked about curvature last, so we'll move from left to right. Okay, the component of A in the direction of your unit tangent vector, well, the unit tangent vector is a unit vector. If you understand the triangle involved with projection, which I've kind of indicated here, you see that the projection of A on t is the signed displacement from here to here. It's not a vector, it's a number, but it could be positive or negative depending on whether the projection goes in the same direction as t or in the opposite direction. Now in this picture, I'm going to mess that all up, but that's supposed to be an arrow. The green vector is your unit tangent vector. This distance is, okay, this is the projection, your projection line down to the direction, the line of the unit tangent vector. And this is the scalar projection, A dot t. Simply this side of the triangle formed by a line along t and the acceleration vector and the perpendicular projection. Very clear that if this is the angle between t and A, the angle here, that this is then the magnitude of A times the cosine of that angle. If the vector A was back this way, so the projection is in the direction opposite t, of course, that would mean that the cosine of the angle is negative, and the scalar projection, A dot t, would be negative. If you multiply this scalar projection by the unit tangent vector, you get this vector, which is called the vector projection. Okay? So, the scalar projection is called the parallel component of A. It's the component of A in the direction of the unit tangent vector t. So A parallel is just A dot t, has very clear geometric meaning. Your acceleration's in this direction, unit tangent vector's in this direction, then you project this vector onto this and you get a scalar here that might be positive or negative if the unit tangent vector is in this direction. If A is back here, unit tangent vector is here, then the projection is back this way. To calculate it, all you have to do is do the dot product of A with t, because the dot product of A with the unit tangent vector is the magnitude of A times the magnitude of t times the cosine of this angle. Magnitude of t is 1, so the dot product is magnitude of A times the cosine of theta. In other words, the length of this vector times the cosine of this vector, which is this distance. And you need to understand the scalar projection in terms of that triangle. Okay, well, here's the scalar projection, and we can calculate it. We can do A dot T. Here's your A, and here's your unit tangent vector. A has only a k component, so you only have the k component of this vector, which is just going to be this over this. So here it is, this divided by this. And that's multiplied by k, but of course the projection, when you do this, you got a k dot k, which is 1. It's not a vector. So here's your scalar projection, which we write this way as projection of t on A. Not projection of A on t, projection onto t of the vector A. The vector projection is just what you get if you make this scalar projection into a vector, and you do that just by multiplying how far this is by the unit tangent vector. You get a vector in the direction of the unit tangent vector, whose magnitude is this side of the triangle. So, to get the vector projection, you multiply the scalar projection, A dot t, or A parallel, by the t vector. That's the projection onto t of A, scalar projection, multiplied by the vector t, and we designate that as the vector projection, projection onto t of A, but with an arrow over the projection. So, without the arrow, it's the scalar projection, just the number, how far it is from here to here, but negative if this point is in the opposite direction of the unit tangent vector. Okay, the unit normal, then, well, if you look at this picture here, where you have the acceleration A, you have A dot t multiplied by the unit tangent vector down here, this vector. If you add this vector to this vector, you get this vector. It follows that if this plus this equals this, then this equals this minus this. So this vector here is A minus A dot t times t. It's your acceleration vector minus your vector projection of the acceleration vector onto the unit tangent vector. And it's perpendicular to t because this is a projection. This is obtained by projecting this down here, so it's projected at a right angle as indicated in the picture up here. It follows then that A minus A dot t times t divided by its magnitude is a unit vector perpendicular to the unit tangent vector, and this is going to be your unit normal. I could have written this as A minus A dot t times t. Could also have been written as A minus the projection onto t of A. And this is my A minus the vector projection onto t of A. So here's the vector projection of t onto A, do A, and then add that to negative this vector, you get a vector here, which is identical to this vector. Okay, so there's your unit normal calculated without having to take the derivative of this thing, which is a pretty hairy derivative. Not impossible, easy enough to take the derivative, but very tedious. Takes a lot of board space. Took too much board space for me, so I got kind of messed up trying to fit it onto the board and skipping steps. Anyhow, you can do this derivative, and it's good for your soul to do one. This would be a good one to try. And then to compare with what you get if you do this. This is, hairy enough in its own right. Neither one of them is a simple, it's a simple calculation because it's just plain calculus, just with power functions and square roots and stuff like that. But there's a lot to it, a lot of pitfalls, and we always tend to fall into those. Okay, so here's another summary of what I said over there. A unit normal is A minus a vector projection of A, this picture, divided by the magnitude of A minus that vector projection. Or N equals A minus vector projection onto T of A, same thing I wrote here, but in symbols, divided by the magnitude of that thing to make it a unit vector. So there's your normal vector. Now, writing it out, this is not particularly hard to understand. Calculating it, as I said, and pretty much demonstrated by the fact that I couldn't really get it done on the board space I had, and with whatever mental acuity I brought to the situation. Oh, there it is. This is your unit normal. That's this, that's this. It's also the derivative of your unit tangent vector. The binormal then, you just cross this, cross T with N. It's going to be messy. And then you could, for example, figure out the rate at which the binormal is changing, which means taking the derivative of that complicated expression. Simple enough, but difficult to pull off. And that's no excuse for, the fact that I didn't get it done. Okay, there's the picture. Okay, we'll go on and talk a little bit about curvature.